Jacobian, I think.
I did examples last time. I think we're done with Jacobian. Yeah, those weren't bad. All right. So I put some. I think I'm not gonna collect any more homework for the rest of the semester because I don't want to. I don't want to grade it. So I did put some problems out of the two handouts that I've given that you should look at. We're going to talk about the ones that are in 26, 4, 5, and 10 today.
So I should write these down.
It's your choice.
Yeah, but then I won't, and then I'm going to wonder what they are, and then I'm going to ask you, and you're going to be like, well, you should have wrote it down, and I'm going to be like, damn, you already have enough reasons to make fun.
Grace just completely played that out, exactly how it would have gone, too. Welcome to Grace's one-woman play.
I know. Joe, I've got it figured out. Are we recording?
Yes.
9.8.
All right. So we've got a few more sections to cover before the end of the semester. We'll cover 5.3 today and probably get into 5.4 as well. And then 5.5 and 5.6 go together. So I'm anticipating that we'll probably be done with new material Monday. I agree.
Is the first page of the final going to be all of the equations?
No.
Damn.
Unless you really want it to be.
Yeah.
As long as you take away that question that was on the front page.
Well, that's not going to happen.
Even still, that raises your average if you know the. Those are free points, everybody.
Dr. Go will have it like be worth 1 point total.
And you know what? That's 1 point more than you would.
All right. So let's talk about how we do these problems involving finding PDFs and doing associated probabilities with random samples. So that's what we're really going to focus on for the rest of this time, is talking about doing, I'll call it combinations of independent and identically distributed random variables. So that's what we're learning by a random sample. So this goes into what we'll be talking about quite a bit next semester as well. All right, so this one's a very, very specific example where we're going to find the density function of the minimum of two observations from a distribution. So basically what we're saying is we've got this density function associated with, I know it says x1 and x2, but think about it this way. I've got this density function associated with a random variable, and I'm going to pick two numbers at random according to this density function, and I want to know what the density function looks like for the minimum of the two values. Okay. We're going to do minimums and maximums today. We're going to talk about basically what we refer to as order statistics today. But let's just start with this particular example. All right. So we've done problems like this before where we just start with first principles. If I want to try to find the density function, the PDF, what's the first principles things that we've been doing for most of the stuff that we've done with continuous distributions? Instead of trying to find the PDF directly, what do we find directly first? The CDF, right? Find the cumulative distribution function and then take a derivative, right? So we can do the same thing here. So I want to know the probability that capital Y is less than or equal to some little y. And then we want to associate this distribution function to the distribution function of the x's. So we know that y is, in this case, the minimum of the x1 and the x2. All right, so for the minimum, this one we have to think about this now a little bit and use some of our properties of probability to help us out to figure out what the answer has to be. For the minimum to be less than or equal to a number, all we need is one of them to be less than or equal to the number, right? There could be more of them, but we need at least one of them to be less than or equal to the y, right? So either x1 is less than or equal to y, or x2 is less than or equal to y, or both of them are less than or equal to y, right? For the minimum to be. That sounds like a lot of work, right? One or the other or both. So instead of doing at least one of them, let's do the complement, right? Let's say that we want to do that the minimum is actually greater than y. Because that's a little bit easier. Yes.
I know I'm confused about words.
Okay.
How is the minimum going to be greater than or less than y when y is the minimum of the two things?
Say that again.
So we want little y to be
Little y is just some number we're picking. We want to.
random number.
It's a random. Yeah, it's just some number. Right. Yeah. It's just representing a number.
Okay.
Yes.
So and then when you say minimum, is that like the
Yeah.
smallest number of the two?
Yeah, the smaller. Yeah, the smaller of the two.
Okay.
And actually, this principle works for any list of numbers that we want. We're just doing an example here with 2 to start with. But I could have done x1 out to xn. Yeah, Grace.
How did you know that y is just any number?
Because that's what I'm plugging into my distribution function. Little y is just it's the input for the distribution function, so it can be any value that I want.
Negative, positive?
It has to be positive because my y's have to be positive.
Does it have to be an integer or is it
Nope.
just any number?
It can be any number. All right. So let's think, why does it make it easier to consider this idea now? How do I know that the minimum is greater than y? What has to be true?
When one or both. Greater than.
Is it or? So I want the minimum to be greater than y? They both have to be greater than y, right? If the minimum is greater than y, they both have to be greater than y, right? So this tells me that would be the probability that x1 is greater than y and x2 is greater than y. And this is where the idea of the random sample comes out. Does it, knowing what x1 is, have any effect on what x2 is? Or vice versa? No. So they're independent of each other. If I have an and probability for independence, what can we do with that? Multiply. Split it apart to multiply, right? So this will be 1 minus the probability that x1 is greater than y times the probability that x2 is greater than y. Right? That was why we wrote it as a complement, because now I have an and probability that I can split up because of their independence. Now this is close to, well, actually I could write this in terms of the CDF, but this is close to now statements about the CDFs of x1 and x2, isn't it?
Yeah.
What's the only difference between it actually being exactly what I would want for the CDF?
It's not always.
Yeah, it's the greater than instead of less than. It's the complement of what I would want, right? We agree? So, to change it back again, we write it this way to start with. I'm only doing this extra step so that you can see the CDF in here.
So you have to do the 1 minus the both of them.
You have to do the 1 minus the both of them. Now, I'm not going to do this every single time. I'm just doing it so you can see the CDF in there. Do you see why I wrote it as 1 minus though, so I can rewrite it as a complement?
So why is it not less than?
Oh, yeah, it would be. I'm not as worried.
It doesn't really matter.
It doesn't really matter because they're continuous in this case, yeah. But you're right, there should be an equal in there. If I'm being technical, there definitely should be an equal there. Yeah, same.
So if we see a problem like this again, then instead of doing all the steps, we can just split it up at the beginning as like multiplying them together.
Actually, there's something that we're going to get to the very, very end, and we'll have a derivation for the formula, so you'll never have to go through it again. But this is why I'm doing it for 2, and then I'll talk about what the general formula looks like for n of them. Okay. All right. What else, besides being independent, what else do we know about x1 and x2? Okay. What else do we know?
Density function, there's PDF is even there.
Yeah, we know that they have the exact same distribution, right? their PDFs are both the same. They have the exact same distribution, which means that this cumulative density function, or cumulative distribution function, is the same as this one, isn't it? Right? So I might as well have written this as 1 minus capital F of x, or I should say capital F of y, sorry, squared, because there's two of them, right? This would be 1 minus capital F of y, and so is this one, because they're identically distributed.
Why do we know that that's capital F, Y, and not capital F?
Because my number that's on the right-hand side here is y, instead of having a little x there. All right, so now let's go back over here. That was our distribution function for y, right? We agree? Okay. How do I get from the CDF to the PDF now? Take the derivative, right? All right, when we take the derivative now, I'm going to use chain rule, right? 2 will come down in front, make that a 1. And then I'm going to take the derivative of the inside, which will be a minus capital F prime. And what's capital F prime equal to? Little f, right? So this will be 2 times 1 minus capital F of y to the first, and then times little f of y. And notice your negatives cancel in this case, right? You have a negative out in front and a negative when you take the derivative of the inside. And that's a 1, not a prime, by the way. I purposely wrote the 1 there because I wanted to talk, I just said that we could do this generally as well, correct? We did this for 2, but what if I had 3? What would change with this whole process if I had 3 instead of 2? Yeah, the exponent here would be a 3 instead of a 2, right? Or if I had a 5, it would be a 5 instead of a 2. Or if I had an n instead of a 2, right? So I'd have an n there and then n minus 1 there. So generally speaking, so let me write the general formula and then we'll go back and find the exact distribution function here, or the density function, I mean. So in general, if capital Y is the minimum of x1 out to xn, then the PDF of y is g of y equals n times 1 minus capital F of y to the n minus 1 times little f of y. Where capital F and little f are the CDF and PDF of x. The random sample, the x1 out to xn, is just taken from a random variable x. It's from that distribution, right? The idea behind being a random sample is that if I think of them as individual variables, they all have the exact same distribution and they are all independent of one another. That's the idea of random sample, right? The random is the independent. The sample is the fact that they all came from the same distribution. Okay? So we refer to, if you want to use a lot of syllables, you refer to it as independent and identically distributed. That's a lot of syllables, right? Random sample is easier to say. Yeah, Grace.
What's the difference between G and Y and F?
What's the difference between them? You mean this function and that function?
The little one.
The little one and this one? Little g is this entire function. Little f is just the PDF for x.
For X?
Yeah, for x.
Plug in y.
You're going to plug in y for the x. So let's go back up to the original example. What was our PDF for x? It was e to the negative x, right? So what's capital F of x then? What kind of distribution is this if it's just e to the negative x? It's exponential, right? So what's the CDF look like for the exponential?
Negative.
I guess 1 minus that, right? Right?
It sounds stupid if I ask for that.
Yeah? No? That's how we do, right? This is your definition of your CDF, is to do the probability up until an X. Probably should have used the T here.
Oh, yeah.
Right? So I just integrated, and that's how you find the function. More better? Okay. Okay. All right. So going back to the minimum then, our little g of y, our random sample was x1 and x2, right? So if I just use this formula we came up with, n is 2, f of y is 1 minus e to the negative y, raise that to the first power, and then times an e to the negative y. Right, I'm just going up and just plugging it into this formula, correct? Well, it was remember in this particular example, y was the minimum of x1 and x2. So n is 2. Right, so I put the 2 here. And then f of y, capital F of y is that one, just with the y replacing the x. And then little f of y is that one. Yeah?
So that goes back to where we did the probability of y.
That one?
Yeah.
Yeah? Mm-hmm.
Is that why we put the little y is why we plugged it in?
That's why we're plugging in the little y, yeah. Yep, that's fine. So what does this become if we simplify this? You get 2e to the minus 2y. The reason why I went through this a little bit more long-winded, if you will, is because I wanted to get to this point where we could see the derivation for the minimum. Does that make sense? Everybody's so happy today. Okay. Let's look at another one here. Yep, not that one. Not yet. Here we go. Let's do this one instead. 26.11.
What was that last one?
26.2? Or 3, I mean. The 26.12 should have been the last one on my list. I didn't do that one last. All right. You're going to record 5 wait times. You want the expected value of the shortest wait time. Well, if I want expected value, I first need a PDF, correct? Since we're looking for the shortest wait time, we're looking for a what of the 5? A min, right? We want the shortest, we want the minimum of the 5 values, right? So each of x1 out to x5 have what type of distribution? So what is its PDF then? Good. Pardon me. We agree? Cool. So, what's wrong? Oh, sorry. We want y as the minimum, the minimum of the x1 out to the x5, right? What you just told me? Okay. So what will the PDF be? What's n in this case? 5, right?
There's 5 times 1 minus big F of that.
Yeah, big F of little y to the 4th times.
1 of the y.
Yeah, that's right in the formula, but yeah, you're right. The F of y, right? So our formula of n equal to 5 looks like this, doesn't it? Okay. And you already told me what the PDF is. Do we know what the CDF is then too? So if I go over here, what is the CDF then? That's 1 minus e to the negative x over 10, right? Yep, it is. If you don't remember it, just integrate.
Is that always true for?
Yeah, for exponential, it's always that way.
It's always just 1 minus.
1 minus e to the negative x over theta, always.
Good to know.
Yes, it is. For exponential, it's a good one to remember because it pops up enough
I
times.
probably should have known that.
Haley's nodding in agreement, so she's probably seen it once or twice on exam P. All right, so if we plug this stuff in over here, then 1 minus capital F of y will be 1 minus the 1 minus e to the negative y over 10. I can write a 10 to save my life. To the fourth, and then times 1/10 e to the minus y over 10. I didn't say it wasn't. That's why I'm not going to bother doing the integral. We're just going to set it up and call it good. Well, yeah. This is not. It's not that bad. You get a 1/2 when you do your 5 and your 1/10. All right. Right? The 5 times the 1/10 will give you a half. The 1s will cancel. So you get an e to the negative 2/5, 4/10. Right? 2/5 and another 10th. 4/10, 5/10, so you just get an e to the minus y over 2. It's not that bad.
Oh, the whole thing is to the fourth?
Yeah, the whole thing is to the fourth.
Oh my, that makes it so much better.
Yeah, it does make it so much better, doesn't
I
it?
really thought the 1 minus e to the.
Ordinarily, we would have to take an integral. In this case, we actually should know the answer.
It's
Wait,
2 minutes.
Yeah, Megan.
The thing that you just wrote, is that with the integral taken, or did you just simplify?
I just simplified it. Yeah, this is just simplifying this math. I haven't done an integral yet,
So,
and I'm not going to either.
what was the question?
I don't know. This is the PDF. What was the question?
Calculate the expected value of the short-term.
Calculate the expected value. So if I didn't recognize what this PDF was, I would have to do an integral, right? I'd have to do the integral over the entire support of y times the PDF. When we're doing expected value, is you take the variable times the PDF and integrate. That's how we do expected value. Why don't I have to do that in this case? That's a PDF of an exponential distribution, isn't it? So what's its mean?
2.
2, because the theta is 2.
Dos minutos. I speak Spanish.
Dr. Joe, can you explain the algebra from how you got e to the negative y over 10 to the fourth times e to the negative y
Yeah, but
over
you
10
actually did.
gives you negative y to the half?
4 halves, or 4/10 plus 1/10 is 5/10. Because you multiply your exponents.
Oh,
so you-
okay.
yeah. Is that one okay? So I didn't actually have to do, now if I didn't recognize the PDF, I would have to do the integral to be able to do the expected value. But in this case, I can recognize that it's an exponential with a mean of 2. And so I'm done. It has to be B.
Yay.
Yeah, Morgan.
So if you didn't recognize that and you did the integral, like what would your support be?
It would be the same as your support for each of your x's. So it would be 0 to infinity.
Oh, okay.
So you would do that if you didn't recognize it. That's how you would get it.
That's all.
Yeah, it's just integration by parts. It's not too bad. It's not too bad. All right, this one okay?
Yeah.
Yeah, Hagen.
So what is it the PDF of?
It's the PDF of this random variable here. It's the PDF of the minimum.
Rawr.
What?
That's not what it is.
All right, let's do 26.6. Similar, but flipped, if you will. Instead of looking for don't worry about it saying calculate the 90th percentile, because we'll talk, well, I want to do that just as a review idea anyway. But don't worry about that to start with. Instead of looking for the minimum in this case, what are we looking for? The maximum, right? Because it wants the largest, right? Or the distribution of the largest in the sample. Okay? So our y is going to be the, I know it says y10, don't worry about that. I'm going to say it's the maximum of x1 out to x10. Just separating the variables from y's and x's. Okay. Again, ignore the 90th percentile for the time being. Well, I wanted to do that for review idea for exam, reminding us how to find percentiles. But again, the idea here will be to first find the PDF. And again, using kind of first principles idea, instead of finding the PDF first, what should we find? The CDF, and then differentiate, right? So if I want to do the CDF again, I want to know that the maximum of the x's is less than or equal to little y. Well, if the biggest has to be less than or equal to little y, what has to be true about all of them? They all have to be less than or equal to y, right? So all of the x sub i's are less than or equal to y. That's a big, long and probability, isn't it? Right? x1 is less than or equal to y, and x2 is less than or equal to y, and x3, and so on, right? But since it's and we're doing a random sample, what can we do with all those probabilities? Multiply, because they're independent again, right? So we can break it up. So writing this in shorthand notation, you're familiar with the big sum notation?
Yeah.
Yep. Okay. Well, a big pi is a big product notation, so I'm going to write it as this way. So big pi is just a product, like big sigma is just a sum. Okay. So it says take the probability that x1 is less than or equal to y times x2 less than or equal to y, and so on up the line. But if I look at those individual ones, those are just statements about what? If I say the probability that x1 is less than or equal to y, what is that? How can I rewrite that in terms of what? What function can I rewrite it as? The CDF, right? This is the CDF of the x's, isn't it? Right? We use the independence to break it apart as a product. Now we're going to use the identically distributed part to write them all as the same CDF, right? So this is just going to be the product. I'm going to write it funky to start with. Of the CDF of these things, right? But they all have the same CDF, don't they? Right? So instead of writing it as a product, I can just write this as a power. So again, this is where both of these steps in the middle here are the independent, that's breaking it up as a product, and identically distributed using the same CDF for each one of them. So that's how it becomes a power of the CDF. Anything special about the 10? No, that was how many of them there were, right? So if this were 5, you would have a 5 here. If this were 20, you would have a 20 here, right? Nothing special about the 10. So in general, to write this down as a general idea again, in general, if capital Y is the maximum of a random sample, then the CDF of capital Y is just going to be G of Y equals capital F of y to the n. That's pretty straightforward, right? That's not bad, is it? Now, how do we find the PDF? Okay, need to differentiate. When we differentiate that, what happens with the n? Comes down, decrease the power by 1, and then what do we multiply by? Yeah, the derivative of big F, which is little f, right? And where again, your capital F and your little f are the CDF and PDF of x. Formulas look kind of similar, don't they?
Yes.
Yeah, look kind of similar. But again, now we have formulas, so we can answer questions without having to go through the derivation each time. Of course, if you're like me and don't like to memorize a bunch of stuff, you end up going through the derivation each time, because that's what I do. I don't bother memorizing the formulas. Okay? It's not hard to go back. This is not a hard thing to go back and do, relative to other things that take derivations. But these are your formulas, right? The nice thing is it really does look like a derivative, right? We brought the power down and decreased the power by 1. You can kind of see the derivative in there. All right, so going back to the original problem then, our n was 10, correct? Right? So we would have our little g of y is going to be 10 times capital F of y to the 9th times little f of y. And in this problem, I don't remember what little f of y was, so I'm going to have to scroll back up. Okay, so it was 3 times 1,000 cubed over 1,000 plus y to the 4th. And your y started at 0. Yeah. Okay. So I need that would be this part. Oops, these were, well, it was a little y anyway. So that's our second part here. I still need f of y, don't I? Capital F of y. In this case, I don't recognize this one. At least I don't recognize this one off the top of my head. So we'll actually have to find it. All right? So it's not hard to integrate, right? Oops. Don't mix your variables. So that would be how this is another good review though, right? This is how we find our cumulative distribution function in general. You integrate from your lowest value in your support up to an arbitrary y. Integrate your PDF. This was not too bad to integrate because if you do a u substitution here, if you let your u equal 1,000 plus t, what's du? It's just dt, right? So basically, I just need to integrate u to the negative 4th, which is a negative 1/3 u to the negative 3, so that 3 will cancel, right? So when we do this, we get negative 1,000 cubed over 1,000 plus t cubed, evaluated from 0 to y, What happens when you plug in 0? What do you get?
1.
You get 1, right? So when we get this, you'll get 1 minus 1,000 cubed over 1,000 plus t to the third, sorry. They did not make this one a nice problem.
Should be 1.
That should be a y, thank you. Yep.
Why did you put the 1 first?
Why did I put the 1 first? Why won't you erase? There we go. Because there's a negative in front here.
Oh, so you just flipped.
I just flipped it, yeah. Whenever I see a negative out in front of something I'm doing a definite integral, I always just put the bottom and subtract the top because it's just flipping the limits.
Whatever floats your boat.
It's what I do. All right, so there's our PDF. Bless you. This would have been actually easier in this problem to stay with a CDF, but I wanted to show you how to find the PDF to start with. That was why I wanted to do this problem, to show how to find the PDF. Okay. I also want to do this as a review for what the question actually asked. But are we okay with finding the PDF? It's just a matter of plugging things in, right? Right? Here, when we put in 0 here, we get 1. And it's the second one, we get a 1 to start with. And then it'll be minus when we get flipping the y. Think about it this way, that negative would flip my limits of integration. So I would do the 1 first and then the minus the y term. Are we okay with the formula? Okay. Let's go back and figure out what the question asked. It said find the 90th percentile. Remember how we find percentiles? Yeah, you would set you would want the integral from 0 up to some p, right? Of your f of x is equal to, I'm going to use x's to start with, whatever that 0.9 is, and you're solving for p.
Why did you choose P?
I just used the letter, because the percentile starts with the letter p. That was why I said p.
Will it be an x value?
Yeah, it'll be an x value, yeah. So in this case, that's why I started this at 0. This really should be whatever your lowest number is in your support, right? We agree? Okay. But if I ignore the fact that I'm doing a percentile, what does this really look like I'm computing? The CDF, right? So you could also do this as solve your CDF is equal to that, right? That's just in general, correct? Whatever the percentile is. Okay?
So we're solving the whole thing, the 10 times that times the 3, or just the 1 minus?
Well, so for our purposes, what are we doing? If I want to use this part, I need the CDF of what? It wants the 90th percentile of the y, right? Right? So what was our CDF for y in this case then? So let's go back up here. So this is the CDF for y, right? Right? Okay. So this was our CDF for, well, the x, if you will, in this case. So this will be 1 minus 1,000 cubed over 1,000 plus y cubed to the 10th. Remember, from when we did this for the maximum, the CDF of the maximum is just the power of how many are in the random sample of the CDF of the individual pieces. Right? That was all we had. We get to the product of the probability that x of I is less than or equal to y, right? So this is the CDF of y, our maximum. And we want to set this equal to 0.9, which is a lot easier to solve as opposed to going through an integral. Yeah, Morgan.
Where did you get the one then?
This part, that was what we calculated here. This is the same thing. That's our f in this case. It's the same thing as what's in here.
Okay, so then our big F of X is equal.
The big F, yeah, and they use the same letter in both places, which is kind of bad. This is this piece up here, just with a y instead of an x. So then you would solve this one for a y. I shouldn't give you. Did you do this to the 1/10?
Yeah.
Shouldn't give you an overflow then. That's weird.
I got one of the answers.
Oh, well, good. That's a good thing. What'd you get?
3641.
So D. The important. I don't really care what the answer is for this particular one. I just want to remind us how do we do percentile and those kinds of things. So in particular, does this part right here, how we got these formulas, does this make sense? Or at the very least, could you use them if you remember them? Maybe. Definite maybe. All right. Okay. And then remembering this idea for finding a percentile, being able to solve that equation. All right.
What did we get?
Sam said he got 3641 and change. I didn't do it, so I don't know.
I don't think I did it like that.
So you would need what? 1 minus 0.9 to the 1/10. You would have to reciprocate that and multiply it by 1,000 cubed. Take the cube root and subtract 1,000. If I did it right.
Plugged it into my numeric software.
If I did my algebra right, I have to take the 10th root to get rid of this. I need to flip-flop sides with these. The y's on bottom, so I need to do the reciprocal of both sides, and then multiply both sides by 10 cubed, and I gotta take the cube root to get rid of the cube and subtract 1,000. So that should be the answer.
Okay,
Should be.
I believe it.
That's what the algebra looks like. Grace is typing it in. We'll see if we get the same answer.
I don't think I did it. I don't even think mine is one of the answers. Although I didn't look.
Yours was.
It was? Was it really?
Yours.
Did you get this one? Did you type this in yet?
Crazy answer.
It's not crazy. You got like 3,500.
Hey, it's the same as what I got. Oh, shit.
There? All right. Let's talk about one more here. Let's look at 2612. All right. So this one says we're going to do a random sample of size 5, and we want something about the third order statistic. So what we haven't talked formally about what order statistics are, but we have defined 2 of them. The minimum and the maximum are order statistics. The idea behind order statistics is that you take a random sample and you order them. I know. All right, so in this case, you've got a random sample of size 5. So if you think about order statistics, I would have a smallest, a second smallest, a third smallest, a fourth smallest, and a fifth smallest, or the biggest in this case. Okay, that would be for this particular case. So in this case, when we're talking about the third order statistic out of a sample size of 5, there's probably a simpler name for that. What are we looking for? The median, yeah, the one in the middle, right? So we can actually calculate a PDF for the median from this idea, or for any of the order statistics, using the same kind of ideas that we talked about for finding the order statistics, the PDFs for the minimum and the maximum. Those are also order statistics, right? We would line them up in order. This would be your minimum, this would be your maximum, correct?
It's like a box plot.
Yeah, it is kind of a box plot in this case. All right. So if we want to think about how we would get the PDF, we're going to do this. I'm not going to do the derivation. You can do the derivation. It's a little bit more complicated. But let's think about it, even though it's not technically correct. Let's think about it as if we were doing this for discrete ideas. Okay? If I wanted the probability that y3 was actually equal to a y, what would that mean for the individual pieces? Well, I would need that y3 was actually the y. One of them is actually equal to y, correct?
And y4, y5 greater than y.
Two of them have to be greater than y. Two of them have to be less than y, right? Now, they may come out in a different order, correct? When you select them, they don't have to come out in that order, right? But in general, that's what would have to happen. One of them would have to equal y. Two of them would have to be less. Two would have to be greater, right? Well, how many ways can I pick exactly one of them to be equal to y in this case? 5, right? There's 5 choices. I can make one of them equal to y, correct? Right? Okay. So if I wanted this in this case, I would have 5 ways to make one of them actually equal to y, where I could use the PDF, correct? Now I said I'm doing this intuitively. This isn't how you actually do this in the continuous case, right? Because the probability that you're actually equal to a specific value is equal to what in the continuous case? 0, right? So we're doing this from an intuitive standpoint to derive the PDF. This isn't technically how you do it, but the technical way is a lot harder. Yeah, Morgan.
So like, why are there 5 chances if we're looking at y3?
Because we're looking for the probability that no matter what random sample we take, the third smallest value is y. It doesn't say it had to come out in that order. After we take the sample, we're the ones who put it in order. So the third smallest might be the 5th one you pick. The third smallest might be the 2nd one you pick. We have to do the ordering, so that's where the 5 comes from. There's 5 different ways that one of them could be the y. Okay. All right, so out of the rest of them, how many more do we have to choose from? 4. How many of them have to be less than or equal to y? 2, right? So we would have 4 choose 2 times, what's the expression for random variable is less than or equal to a number? The CDF, right? So this would be capital F of y, and we need both of them to be less than or equal to, so it would be squared. Right? Because I need both of them less than or equal to y. So this is exactly 2 of the 4 are less than or equal to y. Right? And then what else has to be true? Yeah, the remaining 2, which would be 2 choose 2, so I'm not going to bother putting that in there. The rest of the 2 have to be greater than y, and that would be 1 minus your CDF. That's how you would find it. Okay? So if I wanted to do this generally, It's not a pretty formula, but it is what it is. Okay? And it also uses ideas that we've talked about earlier in the semester. All right, so if I'm looking for the PDF of the kth order statistic, whatever the k happens to be, out of n in my random samples, if I'm looking for the PDF of the kth order statistic out of a random sample of size n, I have n ways to make the actually equal to the y value, right? Out of the remaining n minus 1, we're going to choose k minus 1 of them to be less than or equal to y. And then the remaining have to be greater than y. Without that piece on the end, it looks kind of like a negative binomial, doesn't it? Right? It looks like we've got a number of successes and failures and then a success on the last one. Kind of looks that way, doesn't it? Okay. But again, this part is I picked it actually equal to y. This part is some of them are less than y. The remaining are greater than y. So we split it into 3 cases. And that's where that PDF comes from. Okay. Notice this works even if you're doing maxes or mins. If your k is 1, if your k is 1, notice that this is 1, and so is this, right? And then it becomes the formula we had for the minimum. If k is n, this also still becomes 1. This now is n minus 1, and this is 1. And that goes away. So you get the same formula. So this works for maxes and min, too. Okay. All right. We'll talk a little bit more about this next time, as well as get into moment generating functions.